Okay, so I hope you have figured this out. The projection of V onto U, if you graph these two vectors, you may think that, hey, U is not long enough. It doesn't really matter because you can extend U, remember, this is just a direction of U, right? And of course, plugging in the formula is easy, okay? But if you have to find the magnitude and W, I mean, sometimes it helps to graph these. So V is 7, 4, it's this vector here. And then U is 2, 3, but you can extend it. And here is the vector. And you can pretty much tell that the product or the projection you want is actually like this. That's the projection you're looking for. Okay. So how do you find that? Okay, well, to find the projection, you really don't. Oops, I'm in the wrong mode. All right, so the projection of V onto U is, remember, it's U dot V divided by U dot U times U, right? And you may want to just write the formula first so you will remember what to do. What is the product, dot product? It's 7 times 2 plus 4 times 3. You don't have to always write these things. What's U dot U? That's 2 square plus 3 square. And then, ooh, what happened to, yeah, okay. And then U is just 2, 3, right? Because it's in the direction of 2, 3. So this is, of course, 26 on the top, right? It's 14 plus 12. And then the denominator is 4 plus 9, which is 13. And look, oh, that's a nice number, right? This is 4, comma 6. And our picture actually tells you, it looks like it's 4, 6. Right? Because if you bring it down here, that's like 4 here. By the way, here, every square represents a 2 by 2 square, right? And so this is 6. Okay, so the picture indicates that this is the correct projection. And by the way, the magnitude, remember the magnitude of this projection is what I was talking about earlier. This is the length, okay? So you can, I mean, that's basically the hypotenuse times the cosine of theta. So anytime you're looking for the length or the magnitude of a projection, you can use that if you like. It's the, it's the normal V divided or times the cosine of theta. Okay. But of course, you don't know the cosine of theta, right? So you can go ahead and use what we did before. It's this, I mean, think about this. The length is always that thing, which we found. It's the dot product divided by the norm of U. And I said the dot product is 26. And the length of U is the square root of 13. And so that, okay, by the way, I should tell you, even though you were probably told and you were correctly taught to rationalize the denominator, you don't have to do that. I will accept this as the correct answer, okay? If you can't stand having the irrational number in the denominator because you were taught so well in high school, that's fine, okay? This will be 26 square root of 13 divided by 13. And of course, you can do that. And the answer is 2 times the square root of 13. Okay, that is also a correct answer. The reason I don't worry about this thing here is because there's no crime in leaving the denominator irrational. Sometimes it's even desired when you are looking for certain limits, okay? But when you are young, you have to listen to your, high school teacher or whatever. And so, don't rebel. You should do what he or she tells you to do, which is to rationalize the denominator. This is really important in the old days when you didn't have a calculator and you want to try to find an approximation for this number, right? Because how do you divide by the square root of 13? Okay? It's a lot easier if you rationalize any denominator. But in our days, when you have calculators, it doesn't really matter. Okay, W. W would be the vector that goes here. Let me just go ahead and do red here. W is the vector that goes from here to here, right? This is my W. Hopefully you can see that picture. That W is simply V minus the projection. And so what is V again? V is 7.4. And the projection turns out to be 4.6. Take the difference, okay? And you will see that the projection is, if it appears here, yeah, okay, it's 3, -2. And it looks, again, the picture seems to tell you that the projection should be like 3, -2. And that is the correct answer. All right, so again, it's not something that you will have to do every day or many times in this section, but sometimes they will ask you to not only find the projection, but also the length of the projection and the complement, the orthogonal complement. Okay, so finally, I should mention something about work. Yeah, you have to work hard, but that's not what I mean by this. Okay, this is a great way to talk about how important it is to think in terms of a dot product. Okay, so imagine you have this ground, and you have that should be a straight line. Okay, I'm going to draw a straight line for you. Okay, that is supposed to be a line. Okay. All right, and anyway, you have an object. Let's say a box is sitting here. Okay, and you're pulling this with this force, which is V, okay? And you know that work is with capital W. Work is the force times the distance, right? So if you pull something for like 10 feet with a force of 2 pounds, that's 20 foot-pounds, and that's the amount of work. But see, there's something very important about this. When they say the force, this is force, but not the force necessarily that you're applying to it. This is a force in the direction of the motion. All right, D is of course the distance. So when you pull this object like this, and if the object is moving in the direction of V, like for instance, if this box miraculously starts to float up in the air in the direction of V, then this would be okay. But that's not what happens. The direction of how this box moves is actually like this direction, right? So guess what? You would have to project this V onto the horizontal component, right? So this will be, let's call this U, right? So this is really the force that is applied to move the box along the ground. So that's this. Let's see if I can draw this. Yeah, that horizontal vector, which is F, okay, that's the force that we are talking about. And so we have to calculate the projection or the magnitude of the projection in order to find the work in physics. Okay, so as I said, F in this case is the force in the direction of the motion, and so remember this F is of course projection of V onto U. And of course, we have already calculated this. That's U dot V divided by U dot U times U. The force as the scalar is the magnitude of this force. We have the formula for that too, right? What is that? Okay, remember that's the scalar, the length of this project. And we also had a formula for that. That's U dot V divided by not U dot U, but just the scalar, the length of U. Okay, so that's an application of vector analysis in physics, right? So for instance, let's say you have an object here, right? You're pulling it at 100 pounds, the force of 100 pounds, okay? And the angle turns out to be 30 degrees. You don't even have to know all of these, okay? All you have to do is to apply your trigonometry. Say, well, what is the force? The force you're using, the magnitude of the force is, I mean, just think of the trigonometry. That's all you need really for this, okay? It's the hypotenuse times the angle between these, right? because a lot of times u is not given as a vector component. U is just a horizontal line. So using the first semester trigonometry or the first day trigonometry, you can find the length of f, which is the adjacent side, the length of the adjacent side of this right triangle. Okay, so what is that? Okay, well, this is 100 times, remember what the cosine of 30 is? Square root of 3 over 2. And so this is 50 times the square root of 3. And if you pull it, let's say 10 feet, then the work done by this force in dragging this box 10 feet along the floor would be the force times 10, which is 500 square root of 3, and the unit will be the units of foot-pounds. Get that? All right, so I'm going to just make a concluding remark here. If you think about moving this thing here, all right, so what do you have to do? Let me draw another picture of this to give you a more generalized thing. Okay? The box is at the point P, and you're going to move it to the point Q, okay? And you're pulling it in this direction to the force V, okay? So here's my vector, you know, PQ. So what happens? The work here would be, of course, you know, F times D, the force times the distance, right? And I said the force is the magnitude of this projection of V in the direction of PQ. And then, see, that's this scalar F, which is the magnitude of the projection, right? And then, of course, you multiply this by the length of the vector PQ, all right? But just imagine this. What is that thing, okay? Well, the projection of V onto PQ is V dot PQ divided by, or what, remember the length of the projection? It turns out to be divided by the norm of PQ, right? And then you multiply this by PQ. Guess what? Yeah, this kind of goes away. And so if you're trying to find the, it sounds funny, trying to find work. No, trying to find the work, the amount of work done by this vector V along the horizontal or any other vector PQ, then all that you have to do is to take the dot product. Really? Yeah, really. Okay, so the dot product itself is the work done by this force indicated by V. Okay, so we'll talk a lot more about dot products. In fact, in very last chapter, chapter 6, we'll be talking about the dot product and anywhere in between. So the dot product is one of the nicest things because it's easy to calculate. And also it's one of the most useful things as related to the angle between two vectors and so on. And you will see lots of applications of the dot product throughout the semester. All right, so that's it for this section. Now it's time for you to do your exercises. Enjoy, and I will see you next time.